All right, so today we're going to talk about a couple things. First, we're going to start with probability, just as a review. I know you've probably talked about probability in the past. I know we talked about this at the beginning of the year, but it's good to have a review on this, as you will see this on the Keystone. So probability is just, remember, it's the measure of chance of a specific event. Okay, it's expressed as a ratio, okay, of favorable outcomes to the total. This is typically written as a fraction, a percent, or a decimal. Okay, so that's pretty much the basics of just what probability is. So we want to get a little bit more into how to find our probabilities. So let's go ahead and just look. This is just a simple probability problem right here. Okay, it's saying we're giving the probability as a fraction in simplest form for the decimal, as a decimal and a percent. So it's saying the spinner below is used for a game. It's spun once and find each probability. So this P and this parentheses thing that's going on right here is just telling you the probability of whatever. So this is the probability of spinning a 9. I can see on my wheel right here that the only time the 9 shows up is right here. And there are 16 total spaces if you count up all the wedges, or you can see it's counting 1 through 16. So that is a 1 out of 16 chance, and you can divide that in your calculator, 1 divided by 16, to get that decimal of 0.0625. And then the percent, remember you move the decimal point 2 places to the right, 6.25%. Okay, so that's just basic probability. So like probability of at least a 12 in part B, you'd want to look at every single answer that is 12 or more. So 12, 13, 14, 15, or 16. You can see there are 5 different sections there that would fit that. So that probability would be a 5 out of 16. And again, just divide to get that decimal and then multiply that by 100 to get that percent. They might ask you about the probability of getting a perfect square. So you'd have to identify all the perfect squares on this spinner in order to figure that out. I'm not going to go into too much detail. If you have questions about that, please let me know. But I want to skip ahead to slightly more difficult stuff, slightly. So let's go ahead and look at this. We have the complement of an event. So the complement of an event is just the probability of the event not occurring. So if you see something asking for the complement of something, it's just the event or how much it would not happen. Since the sum of all probabilities in the sample space is 1, so the total chance of something happening, you can get 100% 1. The probability of it not occurring would be 1 minus whatever the probability of that event is. So like for example, number 8 says the probability that it will rain tomorrow is 3/8. What's the probability it won't rain? So you would just do 1 minus 3/8, which would get you what? 5/8. Okay. Pretty simple. Change it to a fraction, it's already a fraction. Change it to a percent, change it to a decimal, and you've got your complements there. So there's 2 different types of probabilities. We have theoretical and we have experimental probabilities. So theoretical is what should happen. And experimental is what actually happens. Okay, so theoretical is just theoretically what will happen. Experimental, you're actually doing that experiment, so it's what is actually happening. They might not be the same. So that's a good thing to keep in mind. It's not always. If they're telling you, like, what's the probability of something occurring, that's a theoretical. But if they give you a set of data to use, then that's the experimental probability. So just keep that in mind when you're answering these questions. Oops, didn't mean to do that. All right. So that didn't work. Sorry, I'm using my iPad, so I don't really know how this program works on here. Theoretical versus experimental probability. So in this event, they are wanting you to create both a table of like what should happen versus what would happen, just to kind of show you that it's not always the same. So we're just going to go ahead and skip over that. You might see some examples like this where they give you a table of values, and then you need to just look at this first of all. Like this, the frequencies would be the experimental probability. So like for part B of number 9, it's saying the experimental probability of rolling a 4. So you would physically look at how many times did a 4 show up. In this case, it is just that 5 right here. Okay, so 4 is 5 out of the total number of trials they ran, which was 50. And then remember, if you can reduce, you need to. Okay, so like there's a 1/10 probability of this happening in this experiment. However, theoretically, rolling a 4 should be a 1 out of 6 chance. Okay, because theoretically there's 6 sides. There's a 1 out of 6 chance of that happening. But what actually happened was it appeared 1 out of every 10 times. So just keep that in mind whenever you're working on those kind. But I know a lot of the ones you might see are more along the lines of the compound probabilities. So let's just take a quick review of tree diagrams. I know we've done some problems that involve this. So let's just go ahead and look. The spinner below is spun twice. So you want to have your tree, right? The first time you spin it could be A, B, or C. After that, since it's a spinner, nothing changes here, okay? There's nothing that removes itself. So the second time could also be A, B, C, A, B, C, A, B, C, okay? So here, the total options you can have for your sample space, you could have an AA, you can have AB, AC, you can have BA, BB, BC, you could have CA, CB, or CC, okay? Those are those braces. So that's the sample space. That's all the possible options you could have here in this tree diagram. And then the probability would just be what you see here. So what's the probability of getting a B twice? So that was right here. So that's 1 out of 9. For this next one, it's saying, what's the probability of at least one A? So I would pick every answer that has at least a letter A in it, which would be 1, 2, 3, 4, 5, out of those total 9 options. So 5/9. And then I'm going to use a different highlighted color for anyone that does not have a C. Okay, so no C, no C, no C, no C. Okay, so that there is 4 out of 9. So that's how you could handle a tree diagram. Let's see, fundamental counting principle. So this is just one activity can occur M ways, another activity could occur N ways. So you would just take M times N to find those total outcomes. So for example, to leave her office, Karen can choose between 3 sets of stairs and 7 doors. So 3 different stairs times 7 options for doors. She has 21 total different options she can choose. So if you get something like this, where just how many possible options can she have? If you just multiply those numbers, that'll get you your answer there. So like, for example, number 3, it says the class has 11 boys and 16 girls. How many ways can the teacher choose 1 boy and 1 girl? Well, there's 11 boys and 16 girls, so you just multiply those to get 176. Okay, so that's that idea. So compound events is actually what I really want to talk about. And this is whenever the probability of 2 or more simple events. Okay, so in this case, you have independent events and you have dependent events. So for independent events, this is where nothing's going to impact them. So like you're spinning a spinner and you're rolling a die, or you're spinning 2 spinners, or you're rolling 2 dice. There is nothing that can happen that would remove one of your possible options. So you don't have to do anything special when you're trying to find that probability other than just multiplying your fractions. So like, for example, let me erase this and move this up. So for example, it says for number 1, what's the probability of rolling a standard die twice and getting the even number and then a 5?